In this video, we are going to look at a different aspect of chemical interactions. We're going to look beyond just the qualitative relationships that exist when you mix chemicals together. You mix an element with a compound or mix two compounds together, and leaving it only at describing what is observed. Beyond those general observations, we want to measure what is taking place. We also want to be able to make predictions. And to do that, we're going to have to quantify the chemicals. We're going to quantify the reactants and the products of the chemical reactions. So that's going to be our focus throughout this particular video. The challenge, though, is the scale that we have to deal with. The things that we are going to quantify and try to measure, they're very, very small. We're talking about the atomic and the molecular and ionic level. And if we just reflect for a moment measurements that we've alluded to previously and remind ourselves of the scale that we're dealing with. If you start with an atom, a typical atom, atoms are not all the same size. There is a range of sizes. And an atom typically will range between 1/10 and 5/10 of a nanometer. A special unit that we have created to help make that a little more realistic and more relatable is called an angstrom. And an angstrom is 1/10 of a nanometer. So a typical atom can range anywhere from 1 to 5 angstroms in diameter. That is extraordinarily small. That's 1,000,000 times smaller than the width of human hair. So we're down to a position of dimensions that we just normally don't encounter. We can go further because, of course, an atom has components, and we learned all about the nucleus, and the nucleus is 100,000 times smaller than that. So we've got an awful lot of empty space in an atom, and at a scale that we have a hard time relating to. So let me come up with an example everyday, kind of on the macroscopic level, to try to drive this home. So if we had a hydrogen atom, we know hydrogen atoms have an atomic number of 1, which means 1 proton in the nucleus. There generally are no neutrons whatsoever in most hydrogen atoms. And of course, there would be 1 electron orbiting around that single proton. So if that proton was the size of a golf ball, the electron would be 1 mile away from there. That leaves a lot of emptiness from that position in the nucleus to where the electron is orbiting. So atoms, even the largest ones, the most populated ones with lots of subatomic particles, a lot of it is emptiness. And that's something to keep aware of, and we'll discuss some aspects of that later. So how do we quantify such tiny things? Well, we're going to have to come up with probably some special units of measurement that's going to make that an achievable thing. Here's a diagram, a graphic that kind of illustrates what I was just mentioning. And yet, when we go to quantify these tiny things, we're going to use techniques, approaches that we use even in everyday life, again, on the macroscopic level. One way, we could count things. We could count how many atoms are present, or how many molecules if we're dealing with a compound, or how many ions are present, let's say, in a solution of some ionic compound. Counting, that's one way that we quantify things. In everyday life, when we go to purchase things, we often are purchasing them based on how many do we want. The grocery store, the supermarket, is a great example, offers up lots of examples of the way we count things. So I could go and I could purchase, let's say, 5 donuts. Okay, that's one way of counting. I can actually count the number of donuts that I am buying. Or I'm going to buy 2 packages of breakfast cereal. So that's one way we quantify things. While I'm at the grocery store, I might measure things in mass. A number of things are measured in mass, or weight, which is, of course, related to that. I go to purchase some apples. Usually they're not sold by how many, they're sold by their weight, their mass. I can weigh them. Next to the apple bin, there will be a scale that lets me weigh the apples that I have packaged up, and so I have an idea of what I'm going to have to pay for them. Or some of the things I might buy are going to be measured out in volume. I buy a pint of milk, a quart of milk, a half gallon, a gallon of milk. It's sold by volume. A lot of times, liquids in particular are measured by the volume that they occupy. So, everyday life, definitely. We can count things, we can weigh them, we can measure their volume. We're going to try to do the same thing with these really tiny things called atoms, molecules, and ions. So let's first of all zero in on counting. If we're going to count them, how would we go about doing that? How is this going to happen? Here you see in the photograph, the photo micrograph of looks like some salt crystals here. Very similar to salt crystals we examined under a microscope in our own lab at the very beginning of the year. Nice, regular, repeatable little crates stacked on top of each other. And we could have counted the individual grains of salt. It might be a little bit tedious and it might take us a little while, but we could definitely do that. But you got to keep in mind that even just an individual single grain of salt within it contains 1.2 times 10 to the 18th atoms. So sodium and chloride ions. That's huge. There's no way for us to count those. Even if we could visualize them, we could never count to that big of a number. So clearly we need a special approach to doing that. And in comes what is known as the mole. A mole is a collection of things very similar to a dozen that we use in everyday life on the macroscopic level. A dozen is a collection of things, or a baker's dozen is a collection of things. Well, whereas 12 or 13 things works in everyday life, on the atomic level, obviously it would not be very useful. And that's why we have come up with the mole. Chemists have come up with what is called Avogadro's number of items. 6.02 times 10 to the 23rd items. Defined originally in terms of carbon, because carbon is very plentiful in our environment and serves very well as a benchmark. We won't go through how they actually derived the value, but again, it would have been done experimentally, and we come up with an agreed upon value that will represent a mole. So a mole of anything would be 6.02 times 10 to the 23rd things or items. If we're dealing with atoms and molecules, when we get that many things, that many atoms or molecules, we've got enough of the chemical to see it with our naked eye, to hold it in the palm of our hand if we wanted to, and to manipulate it, to mix it with other things, dissolve it in water, allow different chemicals to mix and react with each other and observe those reactions. So we're on a level where we can deal with them. We can deal with the material. Clearly, too large of a number to be determined directly. It was determined experimentally and therefore somehow indirectly. And a key aspect of this evolved after Robert Millikan's work. You read about him, you viewed a video about him in the fall and his oil drop experiment. But being born out of that experiment was an avenue for experimentally determining the value of what we call Avogadro's number. This is an enormous number. You could never count this high. You could spend all your life counting every moment of your life, and you would not come anywhere near this value. So again, must be determined indirectly somehow. To drive home how big of a number we're dealing with, though, let's relate it to scales that we are used to and that are more relatable. For example, if you had a mole of marshmallows, you'd have enough marshmallows where you could cover the entire United States to a depth of 600 miles. I mean, think about that for a moment. If you just filled your bedroom at home with marshmallows, that'd be a lot, and that's nowhere near the entire United States. So we're talking about a phenomenally large number. Related to computers and counting. A computer can count somewhere at the rate of 800 million counts per second. So you could program a computer to start counting, and it would take them 25 million years to count to Avogadro's number. That is just an incredibly, incredibly large number. But when you're dealing with tiny things like atoms and molecules, it gives us enough of them where we can actually start to manipulate them, and you wouldn't have an outsized situation like you do with the marshmallows and the computer counting. Later on, when you have time, I'd like you to solve this problem here. Again, to kind of give you a perspective on how big of a number a mole is. And when you got a chance, do this on some scrap paper at home. And when you come up with your answers, feel free to email me, and I'll email back to you the answers to this. But the problem is you've got a mole of pieces of paper. All right, so Avogadro's number of pieces of paper. And if you know that a single sheet of paper is 8 thousandths of an inch thick, how many miles would a stack of 1 mole of sheets of paper, how many miles tall would that stack be? After you find that, figure out that if you were to travel from the sun out to Pluto and back to the sun again, how many times could you complete that round trip? How many round trips would be contained in the number of miles that you calculated in the first part of this problem? Try that on your own. Do the work on some scrap piece of paper, and when you got a chance, email me, and I will email back to you the correct answer, and you can judge how big of a number we're dealing with. All right, so anyways, that's one way we can count things. We can actually try to count how many atoms or molecules or ions are present. Again, we won't do this directly. There's going to be an indirect way of accomplishing that. But another way of quantifying matter is through mass. How much material is present? But again, we've got a challenge to overcome, and that is we're trying to find out the mass of a very, very tiny thing. So we're going to need, again, another special unit to aid us. And that special unit was the atomic mass unit, the AMU. And again, We're using carbon as our benchmark. And so chemists came up with a way of defining this and arbitrarily took the most plentiful isotope of carbon, carbon 12, and assigned it a value of 12 AMUs. Now remember, when I give you an isotope and I state a value, I'm stating the mass number. And you have to remember that mass number is the number of protons plus neutrons. All right? So if you had a single carbon 12 atom, well, it's carbon, so I can look up its atomic number. It would have to have 6 protons. And if the mass number is 12, then I know it's also got 6 neutrons in the nucleus. And since they are not indicating that this is a carbon 12 ion, it must be neutral, and it would have also 6 electrons, equivalent to the 6 positive charges from the protons. Now, you may not remember, but back in the fall, another thing we looked at was the mass of these subatomic particles. And the mass of a proton and a neutron, while not exactly the same, if you go to 2 decimal places, you find out that, yeah, pretty much they are. There are applications where the difference is important, but essentially, they're pretty much the same mass, 1.67 times 10 to the negative 27th kilograms. While an electron, its mass is much, much, much smaller, about 1,800 times smaller. So the mass of an atom pretty much relies upon the mass of the protons and neutrons that are found in the nucleus. We collectively call them nucleons. And they are going to account for the bulk of the mass. Doesn't mean electrons don't have any mass, it's just that they are not, they pretty much can be discounted in most applications. And so, if you know the number of protons and neutrons, you pretty much have the mass of an atom. And if you think about carbon 12 being assigned a value of 12 AMUs, and if pretty much we can discount the electrons in the atom, then those 12 particles that are in the nucleus, the 6 protons and the 6 neutrons, to have 12 AMUs must mean that each individual nucleon, each individual proton and neutron essentially has a mass of 1 AMU. So you would suspect that when you look at the periodic table and look up the atomic masses of all the different elements, that you would think that you would have whole numbers, because you can't have fractions of protons or neutrons. You either have a proton or you don't. There's no in between. But when you look at the periodic table, you see that all of the values given for atomic masses are fractions, they're decimals. What would account for that? Well, the problem is that, let's take this lump of coal, for example, that's made up of carbon. It's a natural sample of carbon. So, being from nature, that means it's got a full mixture of all the different isotopes that carbon can assume. And overwhelmingly, the vast majority of those carbon atoms will be carbon 12 atoms. But there are at least 2 other isotopes, carbon 13 and carbon 14, that are also mixed in there at a much, much smaller percentage of the population of atoms. So therefore, when I give you that lump of coal, if I want to have a representative atomic mass to utilize in applying it to that to the carbon, I've got to take into account that there is a mixture. And so what you see on the periodic table are the weighted averages of the isotopes of each of the elements. Again, we will go through examples in class so we can practice doing weighted averages, but you know, an arithmetic average considers all of the components contributing equally you can see how that wouldn't work here for carbon. If the carbon 12, 13, and 14 were contributing equally, the arithmetic average, we could do an arithmetic average, and the average would be 13. And yet the periodic table indicates no, the atomic mass of carbon is actually 12.01. Clearly, we had to take into account that the vast majority of atoms composing this lump of coal is actually that lighter isotope carbon 12, and so of course the average is very close to that. Again, we'll do some examples in class later if you haven't done weighted averages previously. So we have atomic mass, the mass of a single atom of an element, but we have other kinds of masses that we have to consider. There's something called molecular mass. Well, again, if you take strictly the words, well, molecular mass sounds like, oh, we're talking about the mass of a single molecule, and molecules, remember, are the smallest particles of a compound. So we're talking about the mass of a single molecule of some compound. How would we go about getting that value? How would we find the molecular mass of a compound? Well, we just have to keep in mind that molecules, of course, are composed of atoms that are bonded to each other. And if we already know, we can go to the periodic table and look up the atomic masses of the individual atoms, then it seems to make sense. Then if I wanted the molecular mass, I just need to take all of the atoms that make up a single molecule. I have to look at what elements are present, how many atoms of each element are present, and then just add them all together, sum them up, and I will have the molecular mass. We're at the atomic molecular level. That value would be in AMUs, just as atomic mass was. A third kind of mass is molar mass. Again, using the words directly, molar mass sounds like the mass of an entire mole of a element or of a compound. So that would mean Avogadro's number of atoms or molecules, 6.02 times 10 to the 23rd. We could calculate the molar mass by multiplying either the atomic or the molecular mass by Avogadro's number, and that would give us a value in AMUs. But earlier in this video, I indicated that when you get to the molar scale, you've got enough material that you can see the sample of an element or you can see the sample of a compound. You probably don't want to use AMUs anymore. You'll want to use grams. And so in class, of course, we can do this calculation, look up the conversion between AMUs and grams, and find the molar mass of a compound or of an element in grams. What you'll find is that the numbers for atomic mass and molecular mass, they serve a dual purpose. They also end up representing the molar mass of an element or of a compound, except instead of being in AMUs, they would be in grams. So again, we'll do examples in class of this and make sure that you have a lot of practice doing those sorts of calculations. And finally, the third and final way that we could quantify things. We talked about volume for liquids like in the grocery store. Well, again, we can do that also for chemicals, for compounds and elements. But this applies only to gases. If we're going to come up with a nice, convenient conversion for molar volume, this will only apply to gases. It will not apply to solids and liquids. If we need to find the volume of a solid or liquid, we of course know the formula for density. Density equals mass over volume, and we can use that to help us out in calculating the volume that either a liquid or a solid occupies. For gases, they pose a little bit of a challenge though, because gases, their volumes depend quite a bit on the environment that they're being held at, the conditions they're being held at. And if you warm up or cool down a gas, it expands or contracts. So I would need to know what temperature the gas is at. I also would need to know what pressure it's at. If I alter the pressure, I'll either compress or allow gas to expand, again fluctuating. So gases, we need to know the conditions under which they're being held at. And so chemists use what's known as STP, standard temperature and pressure, and they define molar volume under those conditions. Alter the temperature or pressure and the volume is going to fluctuate. You won't be able to use the conversion, and that conversion actually is that 1 mole of any gas at STP occupies 22.4 liters. Again, we will go over examples of this in class so that you can see how to perform those sorts of calculations. So at this juncture, we have come up with 3 different ways of quantifying chemicals, quantifying elements and compounds, or ions even if we want to. And but they're all centered around the mole. Molar volume, the mole as far as Avogadro's number, molar mass. The mole is our kind of a link between all of the ways that we will express the quantities of chemicals that we're dealing with. So we have to be able to convert, therefore, between these different units of measurement. And we're going to use that mole as our kind of link to do that. And to make this a little easier, to visualize this for you, I have what's called a wheel diagram that I have handed out here in class. And we're going to use that wheel diagram to help visualize the steps you would have to take in order to perform a conversion for, again, a sample of some chemical that you might be dealing with in the lab or in the classroom. It literally does look like a wheel, all right, and we'll do some examples using this wheel, but here's the wheel, and you can see it is a 3-spoked wheel, and the spokes correspond to the 3 ways that we can express the measurement of chemicals. So 3 ways that we've discussed in this video: by counting the number of items, by determining the mass, or by measuring the volume that a gas occupies. 3 spokes. At the center of those spokes, at the hub of this wheel, is the link that connects all those, and of course that's the mole. So the hub of the wheel is the mole. Everything goes through the center of this wheel. So if you want to use the wheel to aid you in a conversion, you simply have to locate where are you on the wheel. There's 4 positions you could be at. You're either at the hub or you're on one of those 3 spokes. And then you locate where you want to end up, whatever the conversion that is being required. And you follow the arrows to go from your starting point to your end point. And next to every arrow are instructions of how to accomplish that conversion. Very important to use labels on all of these conversions so that you can check that your conversion is accurate and is going to be correct. So, 3 ways to quantify chemicals: count the number of items, atoms, molecules, ions, measure or calculate their mass, measure or calculate the volume of a gas sample that it occupies. We will use this quantifying approach to be able to quantify chemical reactions in the near future.